Today we continue to talk about continuity um, along with the properties of function that's continuous. Let's take a look at the following results first. A function of several variables, so I can use x with an arrow on top of it to denote several variables. So here obviously in this textbook or in this course we focus on two variables, but generally we can say, hey, this function has several variables. It is continuous at a point denoted by a bar. If and only if somehow you can calculate the limit of this function as x approaches a. If you can calculate the limit at this point, and that turns out to be f of a. So notice this is almost identical. This is actually identical to function of single variable. It's just that we have replaced the single variable with multivariable. All right. An equivalent result is the following. Sometimes we call this sequential continuity. Which basically rephrased the meaning of this limit. Once again, let's refocus on function of two variables. So that's the domain. Is in R2. It's the same story in higher dimension, okay? It's the same story in higher dimension, but here we are talking about in two dimension. It is continuous at a point in D, okay? So this point in D is really a point in R2. If and only if the limit of this equal to f of a. But the meaning of this limit means this, okay? The meaning of this limit means this. For any sequence in D, okay? For any sequence in D that goes to A, okay? It goes to this point. For any sequence convergent to that point, and that sequence is denoted by a pair of x coordinates and y coordinates. So this is a point in D. Sorry, this is a sequence in D that converges to the point AB. And you can plug this point, or you can plug this sequence into F. You get a real number sequence. You get the following sequence, right? You plug in xn, yn into F, you get a real number, okay? So this is a sequence of real numbers. And this sequence converges to, well, the limit, okay? So that's the limit. It is supposed to be the function's value at that point. So in this case, it's just f of AB. All right. So once again here, the key here is for any sequence, all right? For any sequence that converges to AB. You plug that in, that is supposed to converge to FAB. So obviously a direct result out of the theorem is if you can find out different sequences, if you can find two different sequences that goes to the same point, but the function's value does not go to the same number, then that'll imply this function is not continuous. So here's an example. Show that this function of two variables, show that this is not continuous at the origin, okay? At the origin. Show that this one is not continuous at the origin. So the idea will be if I can find out two different sequences that both goes to 0, 0, but if I plug that sequence into F, that real number sequence does not go to the same number. So here's the a quick answer. I'm going to consider the following two different sequences that both goes to 0. I'm going to let x let x to be x sub n, and let y sub n to be m times by x sub n, and by let x n goes to 0. So this is obviously a path along the straight line. Okay, this is obviously a path along the straight line. If I let x n goes to 0, this pair, okay, this pair obviously goes to 0, 0. And then I try to plug this sequence into F. And here's what I'm looking at. I'm going to plug this in. 2xn squared mxn over xn to the power of 4 plus m squared xn squared. Alright. So I want you guys to give it a shot and find out what the limit of this is, okay? It turns out this is just a real number sequence where xn goes to 0. Okay, you're gonna let xn goes to 0. This turns out to goes to 0. You're gonna need to verify this by yourself. And then I would choose a second path. I still pick a sequence of x values that goes to 0, and I pick the y sub n to be xn squared. So obviously this is also something that goes to 0, 0. Alright, if I let xn go to 0. And then I plug in this pair, okay, I plug in this new pair into F. And here's what I'm looking at. Two xn squared, y sub n is xn squared, xn to the power of 4, okay, because it's a square on the denominator. This is actually a constant, alright, this is actually a constant sequence. It goes to 2. Goes to 2. So in this example here, we found two different sequences that both goes to the origin, but the function's value goes to two different numbers. And that's how I can claim, thus, it cannot be continuous at the origin, okay? At the origin. So continuity. So now I'm ready to talk about some properties associated with continuous functions in higher dimension, okay? So many of the results that you're about to hear will sound familiar. But before I start talking about those results, I want to talk about the meaning of a compact set. A set S is compact if, so this is a general definition of compact set. if any sequence, so we're going to denote this sequence by xn. That's obviously wrong because this is a single numbers, so we'll put an arrow on top of it. So for any sequence in R2, if any sequence has a subsequence, that actually converges to a single point in S. So this is the general definition of compact set, and you will hear the meaning of compact set over and over again in a higher level analysis course, but this is the first time you hear it in this course. Compact set, that's the general definition of compact set. Any sequence has a subsequence that converges to a point from that set. Okay, that's the key here. One thing that I like to remind you is actually turns out in R2, a compact set means it is both open and closed. So that makes it easier for us to understand. So let me talk a bit more on the meaning of compact set. Sorry, this is wrong. It's not both open and closed. It's both bounded and closed. All right, bounded and closed. Compact set in R2, it is identical to a closed interval in R1, say from 0 to 1. Okay, so this is R1. So this is a compact set in R1. A compact set in R2, as I said, is supposed to be bounded and closed. So for example, a set like this in R2 that is both bounded, so where the x value and y value are both bounded, and it's being a closed set. This is also an example of a compact set. The general meaning of compact set is defined by in this definition here. Okay, any sequence that has a subsequence converge to point in S. So let me give you another example in R2 that's not compact. If I make this set to be like an open set like this, where all the points inside is included, but not the points on the boundary. So this is what S is. And that's a perfect example of a set that's not compact. And we can verify this with this definition here. The definition says any sequence has a subsequence converges to this point. What if I pick a sequence that goes like this? Okay, what if I pick a sequence that looks like this? Here's one point, here's another point, and it's getting closer and closer and closer to some point on the boundary. So for this sequence, did you notice? Yes, it does. There will be a subsequence that converge, but the limit point A, okay, the limit point A, it is not part of S because we have removed the point along the boundary. You know what I'm saying? So here's a sequence. In S, there is a subsequence that converge, but it does not converge to a point inside S. Instead, it converges to a point on the boundary here, but that's not part of S. That's why this guy is not compact. In R2, because there are many other different spaces that you can talk about compact set, but in R2, keep in mind, the meaning of compact set means it's both bounded and closed. All right. This is comparable to the bounded and closed interval in R1, which is a compact set as well. All right. So repeat this a couple more times in your head. A set that's both bounded and closed will be compact. So now I'd like to make some conclusions for continuous function on higher dimension. Let's think about continuous function on R1. if I have a curve like this, f of x, that is continuous on a bounded and closed interval, then it's pretty trivial that f of x will be bounded. Okay, will be bounded. It is a different story if the set is not bounded and closed. For example, if this set is open and the function is supposedly continuous everywhere inside like this, except it's not required to be continuous on the boundary, then this guy is not necessarily bounded. Okay, so this example here, it is not necessarily bounded. So obviously, for this guy to stay bounded, not only I need this guy to be well continuous, but also I need the interval to be closed and bounded. So that's where we get this boundedness theorem. Boundedness theorem. Boundedness theorem. If I have a function in higher dimension, it's continuous on what kind of a set? S. Then f is bounded on S. Or equivalently, there's a constant k such that the function's value is bounded by k for all x in S. So the function stays bounded. So once again, if f is continuous on what kind of set? Based on what we're talking about here, in one dimension, for a continuous function to be bounded, I need the interval to be bounded and closed. If I remove one of those conditions, if it's open, then it's not necessarily bounded. If I remove the set, the fact the set has to be bounded, then f is not necessarily bounded either. All right, and so it turns out I need the set S to be, well, compact. Any continuous function on a compact set will be bounded. Boundedness, okay, boundedness. So let's now try to prove this. How do I prove a continuous function compact set to be bounded? Well, let's try to prove this by contradiction. Suppose the function is not bounded. So that means, the function's value will eventually cross any number. Then for any n, for every natural number n, there is a point from S, because we are talking about set S here. So there is a point in S such that the function's value at that point is getting bigger and bigger. Okay, it'll eventually cross n for n equal to 1 and 2 and 3. So here we're talking about, hey, there is a point f of x1 that's bigger than 1. There's another point that we call x2 that's bigger than 2. So here we create a sequence in S. Now because S is compact, any sequence has a convergent subsequence. Has a subsequence. So pick out of it, denoted by this as usual. Has a subsequence that converges to A. But here's the key. This point A is not a random point. It has to be inside S. It has to be part of S. Okay, so that's the key here. Okay, that's the key. So now let's think about what does that imply. Here's where continuity comes into play. Okay. F of x, it is continuous. So remember one of the results we talked about a little while ago? For any continuous function, then for any sequence that converges to a point, the function's value of that sequence has to converge to, well, f of a. All right. Thus, the limit of the function's value at that subsequence. Down here, I can say letting k goes to infinity, which is equivalent to nk goes to infinity. The limit of this has to equal to f of a. Now, f of a, this is a finite number, okay? This is a finite number because a is part of s. So the function's value at this point is well defined. It's finite. However, based on the fact that we choose x and k because xn is a sequence so that f of xn is bigger than n. So however, f x and k is always bigger than what? Nk. So in other words, this is getting bigger and bigger. In other words, the limit of this is, well, this one is getting bigger and bigger. So the limit of this is what? Infinity. And that creates a contradiction. The number on the right is finite, but the limit on the left is infinite. All right? So this contradiction shows f of x is bounded above. Bounded from above. Similarly, we can prove f is also bounded below. It's bounded below as well. By doing the same argument, just apply to a new function, negative f of x, which is still continuous. So just flip the sign, okay? Put a negative sign in front. So that's the first result, okay? That's the first result on a continuous function on a compact set. So the equivalent results for a single variable function is if f of x is continuous on a bounded and closed interval, then f of x is always bounded. All right, so here the difference here is the s here is required to be what? Compact. Okay, compact. Followed by the minimum theorem, extreme value theorem. Okay, extreme value theorem. A function that's continuous on a compact set. then the function achieves, well, the maximum minimum. Minimum on S. Okay. So a single variable function, any continuous function on a bounded and closed interval, for example, all right, any continuous function on bounded and closed interval, it'll achieve a maximum or minimal inside this interval here. So here we're talking about in higher dimension. All I need is for S to be, well, compact. Okay, for S to be compact. Once again, in general, we try to treat this as a what? As a bounded and closed set. Okay, bounded and closed set. So on the xy plane, for example, if we are talking about function of two variables here, you are looking at a set that looks like this. Okay, it needs to be bounded and closed. So this is S. Then any continuous function over, okay, over this set, it'll achieve a maximum minimum on this set or in this set. Okay. Let's try to prove this, shall we? Let's try to prove this, shall we? This is a brief proof, does not take too much effort. So the given condition is that f is continuous and compact, isn't it? So direct result is it has to stay bounded, okay? So f is obviously bounded on S. What does that mean? That means f of x for any x in S. So this is a set of real numbers. So basically, you're plugging all the x into f. You calculate the y value, the function's value. This set will be bounded. Okay, it's bounded. So this is a bounded real number set. Well, by what we learned in analysis 1, the so-called completeness axiom. Any bounded set has a supremum and infimum. Okay, completeness axiom. There is a supremum of f over set S, okay, over set S. This is just one way we can write it. Or you can just write this whole set back there, okay, and we call this supremum capital M. And similarly, the infimum is also a finite number. We just need to show that the supremum and infimum are achieved in S, okay, in S. So here's our goal, okay. Our goal is to show the following, okay. We need to show that there is a point that's actually in S such that the function's value at that point equal to the supremum, equal to M. Same story for infimum. So here we're gonna just show this. But then we have to think about the mean of supremum. Okay, we have to think about the mean of supremum. For any natural number n, there's a point in S such that f of x n. So because m is supposed to be supremum, if you think about the mean of supremum, that means there is always a point from S. So that the function's value at that point is very close to M. Okay, it's very close to M. So f of xn will be very close. In this case, is m bigger than m minus 1 over n. So here's f of x1, f of x2, and f of x sub n. And up here is supposed to be the supremum of f. So the y value, okay, all the y values, they can get very close to m. So there is always a point that's not too far away from m. For those who didn't see this, this is equivalent to say, m, the difference between m and f of xn is less than 1 over n, okay? It's less than 1 over n. So if you don't get it, think about this, okay? Think about this. So this is actually the meaning of supremum, okay? The meaning of that m being the supremum implies this. Now S is compact. So there is a subsequence converges to a point A that's in S. That's the meaning of a compact set. So now let's take a look at f of x and k. All the f of xn is bigger than m minus 1 over n. Now this is a subsequence. So we'll just replace n here with nk. So this is supposed to be bigger than m minus 1 over nk, whatever nk is. Now nk could be a number from 1 to 100, for example. And this is always less than, less or equal to m, because m is the supremum. So now we'll pass the limit. Let k goes to infinity. Well, if you let k goes to infinity, this guy, okay, f of x and k goes to f of a. So this one goes to f of a by continuity, okay, by continuity. So this guy goes to m. This is also less or equal to m. So if you pass the limit, you will find out f of a has to equal to m, okay, has to equal to m. Has to equal to the supremum. Has to equal to supremum. Alright, so this is squeeze theorem in reality, okay? If you let k goes to infinity, this guy goes to f of a. But f of a is always less equal to m and greater equal to m at the same time. So squeeze theorem. So f of a has to be m. So that's the results for a continuous function on a compact set. It'll achieve the maximum minimum on S. Additional topic. Some of you might recall the so-called uniform continuity. Uniform continuity. Some of you may remember that in R1, okay, in R1, if you have a bounded and closed interval, then any continuous function on this bounded and closed interval implies uniform continuity, provided that the set is what? Bounded and closed. So here we have the same results in higher dimension. I'd like to talk about this. In higher dimension, just replace this bounded and closed interval with what? Well, a compact set, okay, compact set. So the compact set in general is equivalent to the bounded and closed interval in R1. So that's something you can always compare with and get a good understanding on all the results. So we call this uniform continuity theorem. That goes a simple like this. Any continuous function on a compact set is uniformly continuous. And we can write down the equivalent definition for uniform continuity. It looks pretty similar. Give any epsilon, there is a delta that depends only on the epsilon instead of on where you are talking about continuity, such that whenever the distance between x and a, in one dimension we simply have x minus a absolute value. In higher dimension we take its norm, which measures the distance between the 2 points. Whenever this is less than delta, that's really just depend on epsilon, such that this implies f of x minus f of a, and this difference will be less than epsilon. Now these are real numbers, okay? These are no longer in higher dimension, so you just need the absolute value here. Just need the absolute value. And now I will provide a brief proof for this using contradiction. Okay, using contradiction. If it is not uniform and continuous, let's think about what that means, okay? Then there is an epsilon. We can find two different sequences. One is called xn and the other one is called y sub n. They are both in S. Such that even though they are very close to each other, okay, even though they are very close to each other, but the function's value, the difference in the function's value, instead of less than epsilon, but it is actually bigger than epsilon. So even though x and yn, they're getting closer and closer to each other, but the function's value, they're not staying close. They're bigger than this given epsilon. Well, but because xn, y sub n, they're in this compact set, okay, so there is a subsequence. They are compact sets. They are on the compact set. So there is always a subsequence that converges to the same point. Thus, you can easily calculate the function's value at xnk, and the function value yn k, because this goes to what, f of a. Okay, this goes to f of a. This also goes to f of a. So the limit of this, okay, the limit of this goes to 0. Goes to 0, and that's a contradiction. Up here you are saying the difference is bigger than epsilon, but in reality, the fact that it is continuous on a compact set leads to this conclusion. So that's a contradiction. Okay.